Welcome you all to this lecture. Today we are diving into Unit 10 of Numerical Methods, focus on partial differential equation, or we can call it as PDEs. This unit is critical for understanding how physical systems involving change in multiple dimensions like temperature or pressure are mathematically modeled. We will cover several key sections in this unit, starting with the Laplace equation, its solution techniques, then move to heat conduction equation, and exploring both explicit and a simple implicit method used for solving these equations. Now to begin with, let's recall a derivative gives the slope or rate of change. In PDEs, our function is more than one independent variable, hence we deal with partial derivatives. Now in contrast with ODE or ordinary differential equations involve derivatives with respect to single variable, here we have a derivative with more than one variable and we call it as partial differential equations if they are written in terms of equation. Now PD is essentially an equation involving partial derivative of unknown function. We usually encounter them when modeling systems that vary in both space and time. So these are few examples of PDE equations. Now PDE solution can be represented three ways. So you will often see PDEs represented on grids. These grids usually dependent variable like temperature across different spatial and temporal points. But you can divide into three parts. First one is that you have a different curves with different variation of spatial parameter and temporal variations and plot on a single two-dimensional plot. Second is the two-dimensional, where you can consider two parameters at a time and you have a 3D plot here. Last one normally used a lot is the grid one. So it provides us more flexibility to have more variables to work with. Now most of the PDEs we will study are linear second order equation which have a general form involving mixed partial derivatives. So look like this equation that is with coefficients a, b, c and d. Now understand this form help us recognize and classify PDEs. So we can have a different PDEs. So if we can have only second order derivative involved for x and y and is equal to 0, we call it as Laplace equation and it is categorized as elliptic. Similarly, if we have variation in time and with the space, we call it as a parabolic and it is used for heat conduction. Last one is hyperbolic, where we have x and y variations. Now these are Laplace equation, heat conduction equation and wave equation. So these are few examples and few applications where these PDEs are used. Now we will start with the simple equation, the first equation, elliptic one, that is known as Laplace equation. So Laplace equation, we start with the Laplace equation, a type of elliptic PDEs. It often models steady state scenario like a heated plate. The equation can also be extended to Poisson equation when there is a source term. Okay. If there is no source term, so this is Laplace equation. If there is a source, either is in case of heated plate, either you have a sink or you have a source, then the next equation become Poisson equation. Okay, if there is anything on the right side, we call it as Poisson equation. Now function describing the source or sink of the heat. Now we will look some solution techniques how we can solve these type of equations. Now for solution techniques, what we did actually, instead of solving original PDE equation, we want to replace it and do numerical solve. We will use a finite difference method that gives us an algebraic equation, iterative equation, so that we can use to solve the PDEs. So for that we need to make different points, so that we have to use those points iteratively to find out the next point and so on. So this is the way to solve the PDEs. So how we do that? For example, this is the second order partial derivative. We just represent into a finite difference method. So for both derivatives we do that, and then we put in the equation of Laplace equation. Then after doing this and do some manipulation, and assumption is that delta x equal to y, we come up with this formulation, and we call it as a finite difference Laplace equation. So the only assumption is that delta x equal to delta y, means that the step size in y-axis and x-axis are same. Now we have this involves discretizing the region into a grid and apply approximation at each point, because we need different points. So it's better to divide the area into grid, and from there you can pick the points and solve this difference equation. Now for example, this is a grid, so these are few points. Okay, we also need to specify the boundary condition. These are essential to get a unique solution. So for example, this we have a region of interest, so we can have a boundary here. So this is the one side of the boundary, this is the other side, and the third side. So we need boundary conditions so that we can use that values to identify and solve our difference equation. Let's do an example and see how we can apply this method to solve a partial differential equation. So here in this example, it is required to determine the steady state temperature at all points of a heated sheet of metal. The edge of the sheets are kept at constant temperature 100, 50, 0 and 75 degree. So we know the boundary condition. Now we want to find out using the difference method to values of the heat at all the points. Now what we did actually here, so we divide this grid into 5 by 5. So but it in grid form, you look here, so there are boundaries here, and these are the within the sheet points that are unknown. So red points are unknown, blue points are known because they are at boundary. So we have for example, one side is of 75, other side is of 100, next is 0, and the third side is 50. So you can see that there are some rows and columns where you can look for the points. So there are 25 points here actually, including these corners that are not mentioned here, but they have the same values. Now we will use this grid to solve the problem. Let's see in next slide how we solve it. So what we have here is that, for example, we just pick a part of the grid, okay, and if we want to know a particular node value that is unknown, for example T13, how we do that? We just use the difference formula and plug the value I equal to 1 and j equal to 3. After doing this, we come up with 0, 3, T14, T12, T23 and minus 4 times T13 equal to 0. Now here if you look at, we have some values known. For example, 03 is the boundary value, that is 75. 14 is another boundary value, that is 100, but T12 is unknown, T22 and minus 4 T13 is unknown. So this is where you can find a point in a grid, okay. So let's move to the next point. For example, if we move to 2 3, how we do that? So in that case, we again apply the formula with I equal to 2 and j equal to 3, difference formula. When we do that, here only one boundary point is coming into play, all other are unknown. So in this way you will write all the equations for unknown points that are red marked in previous slide. So when we do that, so applying this formula, okay, so this is the difference formula. Here you have to put I value and j value. So to make it easy, what we do here is that we make this flat and convert these points in terms of I and j only, that is I 3 1 1 3 2 3 and so on. So that is easy, and we call these points as a node. Okay, now for example, node 1 1, if you want to write the equation for node 1 1, just plug I equal to 1 and j equal to 1 in this equation. So when you do that, you come up with this equation. Similarly, as we know that we have a boundary point, so in this equation we just plug the values of that and we come up with this equation. Similarly, we can find all the nodes points and we come up with this number of equations. Okay, now if you look at these equations, they are around the 9 equations. Okay, so there are most of the values are 0 here. So now the thing is, there are different ways of solving this type of problem. One method is that you can use some Gauss method to do it for elimination, or there are other methods as well. But the issue is that when you do that, it took too much time to do it. So we will want to look some other way around so that we can easily solve these type of problems. Now this is the system of equation that you need to solve it. Then you can solve it. It's a very small system, it's okay, but if you have a very big system, then it's very difficult. So then we will move to another solution technique, which is a numerical solution technique, and we call it as Liebmann method. So most numerical solution of the Laplace equation involve systems that are much large in size. So for example, if you have a 10 by 10 grid, then you have 100 linear algebraic equations. So this is a big number. So the issue with this type of big number is that 5 unknown terms per line in the previous solution, and we have a lot of zeros. So this means the significant number of terms is 0, and we need a lot of memory where we just store the zeros to represent our matrix. So this is a problem that we need. We waste great amount of computer memory storage using these zeros, and also because of sparsity, we want to exploit the sparsity, but we are unable to do it, but we have to compromise the memory location. So what is the solution? So for this reason, we have approximate method provided viable approach. So we solve iteratively using formula like Liebmann method, a form of successive over relaxation that improve convergence. So what this formula is, we continue iteration until change. In Liebmann's method, what we did actually, we just replace Tij and just rewrite the difference equation first, and then overrelax the new point find, so that where convergence is improved. So we continue iterating until change between steps fall below a certain stopping criteria. Also note, while temperature is the primary variable, secondary variables like heat flux may be more relevant dependent upon the application. So what we did actually here, first we just rearrange this equation which was previously discussed, and next is that when we find a new value, we have to apply this method. So what this method do actually, this will over relaxation that will increase the convergence rate. So if you find any value here, you have to plug in this formula to calculate the new value. Now you are calculating value at each point. Now the question is when you stop it. So in that case, you need a stopping criteria. So what we have here is that we have to find the relative error between the new value of the temperature and the old value. Normally it is given that either you have allow 1% or 2% variation. Similarly, the lambda factor, that is the weighting factor, is between 1 and 2 that you can choose, so that based on how your system will converge. Now in first equation where we have Tij, in Liebmann the main beauty here is that if a point is unknown, you just put 0 there at the first iteration, so and you continue your iteration. So this is the way you will do it, but it took more iterations to actually converge, because after applying this our relaxation, still you need some iterations to do it. So this is the one of the method, because you have to do it iteratively. Now this is a stopping criteria. Okay, now let's do an example very quickly. So example is that you have to use Liebmann's method to solve the temperature of the heated plate of the given figure. Employ our relaxation with a value of 1.5 for the weight. So this is the lambda value, okay, that we use for updating our new temperature, and stopping criteria is 1% relative error. So let's see the same problem with unknown points. So how we use this method? Let's see. Now we have a boundary conditions here. T01 is 75, 10 is 0. Now we will just plug the formula here. Now we start with our node, and this is the updation value that we need to use, and for example we start with the node 1 1. Okay, so just plug I value 1 and j value 1 in this equation. When you do that, you come over this relation. You see that only known value is 75 and 0, other are unknown. You just put 0 here. Now you get the value of 18.75. You didn't use this value for next iteration. Instead you apply this over relaxation. So how you apply the over relaxation? Because the original value is 0, because we don't know the value of 1 1, so we put t old equal to 0 and put lambda value which is 1.5 and solve this equation. So let's see how it works. So look here, lambda is 1.5, new value is 18.75 plus 1 minus 1.5 times old value 0. So we come up with the value of 28.15. So the node 1 1 value is 28.125. Similarly, we will work for the next node, for example 2 1. We again do that, again update the value, and we will do for all the nodes. Okay, so we have 3 by 3 9 nodes here. Okay, so when we do that, we come up with these values. All right, node values. So if you see this, these are the values that we calculate using this formula. Now what we do, we move to next iteration. When we move to next iteration, now we have the values of these nodes. We will use these nodes values to calculate the new value, and so on. So this is the main idea about this. For second iteration, we do a new calculation. Now after that, these node values are updated, and we see, okay, now this is the previous one and the new one. Just look at the percentage error. Now percentage error is 13.5. that not satisfy the stopping criteria, so we have to continue this thing. Now we continue till 9th iteration. For this particular example, we reach the stopping criteria, that is 0.17. Now we will stop it. Now this is the final values we get from this Liebmann's method. So this is the solution that we achieved using this method. So this is all about this technique to iteratively to solve this PDE Laplace difference equation. Now we do have some secondary variables. For example, temperature is considered to be primary variable in the heated plate problem, but we for this case as well, other problems involving PDE secondary variables may also be interest. As a matter of fact, in certain engineering contexts, the secondary variable may actually be more important. Okay, so for the heated plates, a secondary variable is rate heat flux across the plate surface. Now we want to know how heat is moving along the plates and what is its flux. So in that case, we have flux is the secondary, we call it as secondary variable because it is not directly calculated, it is calculated based on the temperature, okay, using formula. Now this is the formula. Using the temperature values that you calculate in previous, you can use these values to identify the flux, okay. Similarly, in x-axis and y-axis and the cumulated absolute flux values and the angle in which this flux varies for positive qx, you can come up with this phase deviations. Now let's do an example where we want to calculate heat flux here in the plate, and we have the coefficient because how heat is transferred based on the material that are using. Now we consider aluminium with a coefficient K dash as 0.49 calorie per second centimeter degree centigrade. So we are considering 40 by 40 centimeter plate. Now as we calculate this using Liebmann's in previously, we use these results to actually calculate the heat flux. Now for heat flux we have to plug this value for x-axis and y-axis. So for node 11, so your heat flux values are 1.022 in x-axis, minus 1.549 in y-axis. Similarly, and the absolute value is a 1.856 calorie per centimeter square per second, and the angle is minus 56.584. So this will tell you how heat is flowing in which direction, okay. So in this way you can find flux for all the points and you can plot here. So this is a secondary variable that can be calculated using the temperature information. Now we will stop here for today's lecture, and we will have another lecture, hopefully next one, that will explain the next part, how we can solve explicitly and implicitly these partial differential equations. Thank you for your time and listening to me. See you soon.